Today we're talking about applying derivatives, and in this case we are finding the curve's concavity. So this is concave downward, and this is concave upward. Remember those. Up, down, down. Okay. So in this, let f be a function whose second derivative, remember, second derivative, so you have to take the derivative twice, exists on interval I. So, if the second derivative is greater than 0 for all the x values in I, it's concave up. If the second derivative of x is less than 0 for all x values in I, f is concave down. Down, down, down. Okay, so here's an example. We have the original function f of x equals 6 over the quantity of x squared plus 3. We take the first derivative, and using our quotient rule, we get negative 12 over x squared plus 3 squared. Simple. Okay, and then we have to take the second derivative. So once again, using the quotient rule, we will end up with 36 times the quantity of x squared plus 1 over the quantity of x squared plus 3 cubed. We have to get some critical numbers for this. Not critical numbers, we have to find our interval for this because it's an open interval. So we set it equal to 0 to get the x values, and x will end up being plus or minus 1. Okay, so you set it up in a nice little chart, like so. So you have your first interval, which is negative infinity, which is less than x, which is less than negative 1. And then we have negative 1 is less than x, less than 1. And then we have 1 less than x, less than infinity. For each, we need a test value. For this one, I chose x equals negative 2. Substituting it into the second derivative, I have that the result is greater than 0, so it's concave up. For this one, I chose 0, and the result was less than 0, so it is concave down. And for this, I chose 2, and the result was greater than 0, so it is up.